Welcome back to the deep dive. If you've been following tech news at all lately, it feels like you're just drowning in jargon.
Oh, absolutely. It's everywhere. AI, ML, DL, LLMs, FMs, PEFT.
Yeah, it's like an alphabet soup. And honestly, it makes it really hard to understand what people are actually talking about.
It really does. It puts up this huge barrier. And we see people mixing these terms up all the time, saying AI when they really mean deep learning, or confusing a specific model with how it learns.
Yeah,
And that lack of clarity, it can really mess things up when you're trying to make decisions, like picking the right technology for a job.
definitely. So our mission today in this deep dive is to cut through all that. We've got this stack of source material definitions, architectures, product details.
Right.
And we're going to try and boil it down into maybe a 20-minute masterclass, something really clear and precise.
That's the goal.
Yeah.
You want to give you the tools to talk about this stuff confidently. We're not just listing definitions, we're drawing the lines between them, showing how they relate, how they differ.
So by the end, you should really get why, say, supervised learning needs labeled data, or why that transformer architecture is such a big deal.
Or even the practical choice between something like Gemini and Gemma. You'll understand the trade-offs.
Okay, let's dive in. To make sense of it all, we probably need to start right at the top, build that hierarchy first, show how these things fit together.
Good idea. Because they aren't really competitors, are they? They're nested concepts.
So, starting broad, artificial intelligence.ai. What's the absolute core definition we need to nail down?
Okay, AI. At its most basic, it's any machine or system that does jobs that mimic human behavior, or tasks that usually need human intelligence.
Like problem solving or making decisions.
Exactly. Problem solving, decision making, understanding language, recognizing things like speech or images. It's programming aimed at getting a human-like result.
You emphasized mimic there.
Mm-hmm.
The sources draw this line between simulating and emulating intelligence. Why is that so important?
It's really about managing expectations. AI simulates intelligence. It copies the output, the result of intelligent actions.
Okay.
It's not emulating it, meaning it's not copying the exact biological process of a human brain. And AI doesn't think like we do. It solves problems like we might, but the underlying method, the algorithm, can be completely different.
Got it. So AI isn't about creating a virtual brain. It's about achieving a similar outcome.
Precisely.
And the applications are huge then. Anything from, medical diagnosis systems to recommendation engines online, robotics, those chatbots you talk to for customer service.
All of that falls under the AI umbrella. It's the biggest category.
Okay, so level 2 down, machine learning, ML. How is ML different from just general AI?
So ML is a subset of AI. It's a specific way of doing AI. The key thing here is that the machines get better at a task without someone having to explicitly program every single step or calculation after the initial setup.
So instead of a developer writing endless if this, then that rules.
Exactly. The model uses complex algorithms to find patterns in data and basically teaches itself how to perform the task better over time. It learns from experience, you could say.
So it negates the need for constant manual reprogramming.
That's the core idea. It learns. That was a huge step up from older AI systems that were often really rigid because every rule had to be coded by hand. ML allows systems to adapt.
Okay, makes sense. Now let's zoom in further. Deep learning, DL. You hear this a lot, and sometimes people just use it interchangeably with AI or ML.
Yeah, that's common confusion. DL is a specialized subset of machine learning.
Okay.
While ML uses algorithms generally, deep learning specifically uses something called an artificial neural network.
Inspired by the brain, right, with layers of interconnected nodes.
Loosely inspired, yes. It has these layers of nodes and information passes through them. The deep part comes from having multiple layers stacked on top of each other.
And why was adding more layers such a game changer? What did that enable?
It really cracked the problem of dealing with complex raw data, especially unstructured data like images or sound.
How so?
Well, with older ML, you often had to do a lot of manual feature engineering, basically telling the system exactly what to look for, like defining the curve of a cat's ear.
Right.
Deep learning networks, with their multiple layers, can learn these features automatically, hierarchically. The first layers might spot simple edges, middle layers might recognize shapes, and the deeper layers can combine those to identify complex objects, like the whole cat.
Oh, okay, so it learns the important features itself from the raw data.
Exactly. And that ability to handle complexity in raw data is why things like really good image recognition or complex language translation suddenly became possible. Most of the really advanced AI we see today is powered by deep learning techniques.
Got it. DL is a type of ML using these deep neural nets for complex pattern recognition. Now, where does generative AI, Gen AI, fit in?
Okay, Gen AI, it's another functional subset of AI. And yes, it very often uses deep learning, especially things like LLMs, which are based on neural networks.
But its defining trait isn't how it learns, but what it does.
Precisely. Gen AI is focused on creating something new. New content, new data, stuff that's original but also realistic. So it doesn't just analyze or interpret like other AI might. It generates
And that generation could be text, like ChatGPT, or images.
text, images, music, even code or speech. And this brings up the idea of modality.
Modality meaning the type of input or output, like senses.
Kind of like senses, yeah. It's the type of content the model works with. A model that only does text is unimodal. Something like Google's Gemini is powerful because it's multimodal. It can understand and process text, images, audio, maybe even video, all together.
So you could show it a picture and ask it to describe it in text.
Exactly. And we're even seeing really specialized modalities, like using AI to generate potential new drug molecules based on analyzing genomic data. That's molecular modality.
Wow. Okay, one more key piece in this section, natural language processing, NLP. It seems to cut across a lot of this.
It absolutely does. NLP is a technique, really a field that blends computer science and linguistics. Its goal is to enable machines to understand human language, the meaning, the context, even the sentiment within text or speech.
It's what makes chatbots or voice assistants actually work.
Right. It lets machines analyze documents, synthesize speech, translate languages, understand commands.
The sources break NLP down into a few functional areas: text wrangling, language understanding, processing. Can we unpack those?
Sure. Text wrangling is basically the prep work, cleaning the data.
Getting it ready for the machine.
Yeah. Converting text formats, maybe removing weird characters, and a really crucial step called tokenization. That's breaking the text down into smaller pieces, tokens, that the machine can actually process mathematically, turning words or parts of words into numbers, essentially.
Okay, so wrangling is cleaning and tokenizing, then language understanding.
This is where the machine figures out the structure and meaning of the language. It involves things like part-of-speech tagging, identifying nouns, verbs, adjectives.
Grammar, basically.
Grammar, syntax, yeah. And dependency parsing, which maps out how words in a sentence relate to each other. Who did what to whom?
And that understanding enables the final step, processing functionality.
Right. This is where the machine uses its understanding to do something useful, like named entity recognition, finding mentions of specific people, places, organizations, dates in the text.
Or sentiment analysis.
Or sentiment analysis, figuring out if the text expresses a positive, negative, or neutral opinion. NLP is fundamental for any AI that needs to interact with humans using language.
That's a really helpful breakdown of the core hierarchy. AI, then ML within AI, DL within ML, and Gen AI as a functional capability, often using DL, and NLP underpinning language tasks.
Exactly.
Okay, now that we know what these things are, we need to talk about how they learn, and that all comes down to the data.
Right. You always hear the model is only as good as its data. So understanding how data is structured is critical. We need to be clear on structured, semi-structured, and unstructured data.
Structured seems easiest. That's like your standard database, right?
Yeah.
Rows and columns.
Exactly. Structured data is neat and tidy. It has a fixed, predefined schema, a blueprint. Think of relational databases like PostgreSQL or maybe Azure SQL. Everything's in predictable tables. Super easy to search and analyze with standard tools.
Okay. Now, semi-structured data gets a bit murkier. What's the real difference here?
The key is that schema. Semi-structured data doesn't have one overall rigid schema for everything, but the individual pieces of data do have some internal structure or relationship.
Like the Lego box analogy in the source. Each brick connects, but the whole box isn't prearranged.
That's a great way to put it. Think of JSON files or XML documents. Each document has its own structure, its own tags or key value pairs.
Like MongoDB uses.
Exactly. Document stores like MongoDB or key value stores. You can still query this data effectively, but you need different tools than standard SQL. It's more flexible, but less rigid than structured data.
And then there's unstructured data.
Right.
Which is most data, right?
Pretty much the vast majority of data generated today. Unstructured data is just stuff. It doesn't have an inherent organization or schema that makes it easy to search or analyze.
Like Word documents, PDFs, emails.
Yep, documents, emails, audio files, video, photos, social media posts, sensor data, often just stored as files, maybe in something like Azure Blob Storage.
And for an AI model to learn from this, you need serious pre-processing first.
Absolutely. You need techniques like NLP or deep learning just to extract meaningful features or information from the unstructured chaos before the main learning can even begin.
Okay, so data structure is one dimension. The other crucial one is labeled versus unlabeled data. This seems directly tied to how the model learns.
It absolutely is. This distinction dictates the entire learning approach. Labeled data is data where a human has already provided the answer or context.
Sometimes called ground truth data.
Exactly. It's the ground truth. Think about images for self-driving cars. Humans have gone through and drawn boxes around everything, labeling them car, pedestrian, traffic light. That's labeled data.
And unlabeled data is just the raw stuff. No human tags.
Just the raw data. 1 million photos, but no information attached saying what's in those photos.
And this difference leads straight to the two main ways machines learn: supervised and unsupervised learning. Let's start with supervised, SL.
Okay, supervised learning is the one that needs that labeled data, the expensive stuff.
Right.
The model learns by looking at examples where the correct output is already known. It sees input X and is told the answer is Y over and over again.
So it's like showing it flashcards. Input, correct answer, input, correct answer.
Pretty much. The goal is for the model to learn the mapping, the function, that turns X into Y so it can then predict Y for new unseen X's.
And this tends to be accurate for certain tasks.
Very accurate for things like classification, is this email spam or not spam, or regression, predicting house prices based on features. Because it learned from the correct answers, its predictions are usually quite reliable.
But the big cost is getting all that labeled data up front.
Huge cost. Time, money, and potential for human bias creeping into the labels themselves.
Okay, so if SL is accurate but costly, what about unsupervised learning, UL? It doesn't need labeled data, which sounds great, but where does it struggle and where does it shine?
Right. UL works with unlabeled data. You just give it the raw data dump, and its job is to find patterns, structures, or relationships on its own.
So it's not predicting a known answer, it's discovering hidden structures.
Exactly. It shines when you don't necessarily know what you're looking for, or the data set is just too massive to label. Think about customer segmentation. UL could potentially identify groups of customers with similar behaviors that you hadn't even thought of before.
So it's good for discovery. What are the typical UL tasks?
Things like clustering, grouping similar data points together, or association rule learning, finding things that often occur together, like people who buy bread also tend to buy milk. Or dimensionality reduction, simplifying complex data by finding the most important underlying features.
What's the downside then? If it finds patterns itself, how do you know they're useful?
That's the catch. Because the machine defined the patterns without human guidance based on correct answers, you absolutely need human review afterwards. Someone has to look at the clusters or rules it found and decide if they actually make sense, if they represent real insights or just random correlations in the data.
So UL gives you discovery and efficiency, but needs validation. SL gives you accuracy on known tasks, but needs labeled data.
That's a really good summary of the trade-off.
Okay, before we move on to the models themselves, there are 3 quick terms about the model lifecycle we should define: the model itself, features, and inference.
Good idea. First, the machine learning model. What is it, actually?
It's the end result, right? Not the training process.
Exactly. The model is the train function. It's the algorithm with all its learned parameters or weights ready to go. You feed it input data, it runs the calculation, and it spits out a prediction. It's the deployable thing.
Okay. And a feature.
A feature is a specific measurable characteristic or attribute extracted from the raw data that's used as input for the model.
So if you're predicting house prices, features might be square footage, number of bedrooms, location.
Precisely. Often, raw data needs to be processed to create these features. Maybe turning a date into days since last purchase, or converting text into a numerical score. That whole process of selecting, transforming, and creating these input variables is called feature engineering.
And that's a critical skill in itself.
Hugely important. Good features make or break a model.
And finally, inference.
Inference is simply the act of using the trained model to make a prediction on new, unseen data. You've built your house price predictor. Now someone gives you the details of a new house, the features. You feed them into the model, and the output, the predicted price, that's the inference. It's the model doing its job in the real world.
Got it. Model is the function, features are the inputs, inference is getting the output.
Perfect.
All right, with that foundation laid, now we can talk about the big architectures powering modern AI, starting with foundational models.
Foundational models, or FMs, these are really the engines behind the current Gen AI explosion. They changed the game.
What makes a model foundational? Is it just about being enormous?
Size is part of it, yes. They are typically very large, but the key is their general purpose, nature, and how they're trained. FMs are trained on absolutely massive, diverse data sets, text, images, code, sometimes audio or video.
And they are pre-trained, right? That seems important.
Crucially important. They learn general patterns, concepts, and knowledge from this vast pre-training data. This makes them incredibly versatile starting points. You don't have to train a huge model from scratch for every single task anymore.
So it's like building a general brain once, and then you can adapt it.
Exactly. That's the idea of transfer learning made accessible. You take this powerful pre-trained base model and then fine-tune it for your specific need with much less data and effort.
Okay, and the most famous type of foundational model right now is probably the large language model, or LLM.
Definitely most talked about. LLMs are a specialized subset of foundational models.
Yeah, and what's the defining characteristic that makes an FM an LLM? The sources point to the architecture.
That's right. The key differentiator is that LLMs specifically use the transformer architecture.
This came out around 2017, and it was a big deal.
A huge deal. Before transformers, models processed sequences like text, mostly word by word, which made it hard to capture long-range context, understanding how a word early in a paragraph relates to one much later.
Okay.
The transformer architecture, with its attention mechanism, allows the model to weigh the importance of all words in the input sequence simultaneously when processing any given word. It can pay attention to relevant context no matter how far away it is.
Which makes it much better at understanding meaning and generating coherent text.
Massively better. That's why LLMs are so good at translation, summarization, question answering, and generation.
So how does it actually generate text then using this transformer?
Fundamentally, it's a prediction machine. It takes your input prompt, breaks it into tokens.
We talked about tokens earlier.
Right. It processes those tokens through its many layers and then predicts the most statistically likely next token, or word. Then, critically, it adds that predicted token to the sequence and feeds it back in to predict the next token and the next, and so on.
So it's constantly predicting the next word based on all the words that came before it.
Exactly. It learns the patterns of language, grammar, style, facts, associations by processing billions of examples during its pre-training.
It sounds very statistical, very mechanical. Yet the output can seem incredibly creative, even show reasoning, which brings up that point about the mystery.
Yeah, it's one of the most fascinating and slightly unsettling aspects. We understand the inputs, we see the outputs, we know the architecture, the layers, the attention mechanism, but the models are so complex with billions of parameters interacting
That we don't actually know how it arrives at a specific answer.
we can't precisely trace the step-by-step thought process for complex reasoning or novel generation. It's like a black box. We know it works, we can measure its performance, we can even steer it, but the exact internal pathway of logic for complex tasks is often opaque.
So we've built these incredibly powerful reasoning engines, but we don't fully understand their internal reasoning.
That's the paradox, and it has real implications we need to grapple with.
Speaking of real implications, let's talk about the physical limits. Tokens. You mentioned the model breaks input-output into tokens. How do they limit what these models can do?
Tokens are the currency of LLMs. Text gets chopped into these pieces, and the total number of tokens a model can handle in one go, its context window, is limited by two main things: memory and compute.
Okay, memory first.
Every single token in the input prompt and the generated output takes up space in the computer's memory, usually the specialized memory on GPUs. If the total number of tokens gets too large, you simply run out of memory. The hardware can't hold it all.
Just like running too many apps on your phone.
Kind of, yeah. And the second constraint is compute.
The processing power needed.
Exactly. The calculations involved, especially that attention mechanism in transformers, get significantly more complex and time-consuming as the sequence length, the number of tokens, increases. It's not linear. It often grows quadratically or worse.
So longer input or output means way more calculation.
Way more. That's why there's always a limit on the total tokens you can use in a single interaction with an LLM service. It's a hard limit based on the hardware's memory and the acceptable processing time or cost. You can't just feed it a whole book and ask for a summary in one shot.
Right, you'd exceed the context window. Okay, so we have These pre-trained FMs, often LLMs using transformers, constrained by tokens. But the pre-trained model is general. How do we make it specific? That's fine-tuning, right?
Exactly. Fine-tuning is taking that general-purpose pre-trained model and adapting it to your specific task or domain by training it a bit more, but on a much smaller, focused data set.
It's like sending the generalist to specialty school.
Perfect analogy. You're adjusting the model's internal parameters, its weights, so it gets better at your particular thing.
The sources mentioned different types of fine-tuning. There was instruction fine-tuning versus domain-specific.
Right. Instruction fine-tuning is about teaching the model how to behave or follow specific formats. You give it examples like input.customer query, desired output, empathetic summary. You're training it on input-output pairs to follow instructions.
Okay. And domain-specific.
Domain-specific fine-tuning is about updating the model's knowledge. You feed it data specific to your industry, your company, or a particular subject, like training a general LLM on recent medical research papers to make it an expert medical assistant.
Got it. One teaches behavior, the other teaches knowledge. And then there's the method of fine-tuning, full versus PEFT.
Yes, this is crucial for practicality. Full fine-tuning is the traditional way. You update all the billions of parameters in the model.
Which sounds expensive.
Very expensive. Needs lots of data, lots of powerful computing hardware, GPUs. Takes a long time.
And parameter-efficient fine-tuning, PEFT.
PEFT techniques are much smarter. Instead of updating everything, you freeze most of the original model's parameters and only train a small additional set of parameters, or maybe adapt some existing ones slightly.
So you're only tweaking a tiny fraction of the model.
Exactly. And the result is often almost as good as full fine-tuning, but the cost, the data requirements, and the time needed are drastically lower.
That sounds like it makes customization much more accessible for businesses.
It absolutely democratized fine-tuning. Suddenly, you didn't need a massive research lab budget to tailor a powerful FM to your needs. PEFT was a game changer.
Okay, this is great. We understand the models, the architectures, the constraints, and how to customize them. Now, how do we actually control them effectively when we use them? Let's get into prompting and parameters.
Right. Once you have a model, getting the output you want often comes down to how you ask. Prompting is key.
It's not just typing a question, is it? There's strategy involved.
Definitely. The simplest approaches are zero-shot and few-shot prompting.
Okay, zero shot.
Zero-shot means you just give the model the instruction and the input without providing any examples in the prompt itself. You rely entirely on its pre-trained knowledge.
Like asking it, translate this sentence to French. No examples needed.
Exactly. It should know how to do that from its training.
In few-shot prompting.
That's where you do provide examples within the prompt. This is sometimes called in-context learning.
So you show what you want.
Yeah. If you want it to classify customer feedback as positive, negative, or neutral, you might give it 2 or 3 examples first. Feedback, example 1, sentiment, positive, feedback, example 2, sentiment, negative. Now classify this. Feedback, new feedback, sentiment.
So you're guiding its prediction with examples right there in the prompt.
Precisely. It helps the model understand the specific task format and desired output style much better, especially for tasks it might not have seen much of during pre-training.
Okay, now what about chain of thought prompting? The sources suggest this really boosts accuracy for complex tasks.
It really does, especially for reasoning problems. Chain of thought, or COT, is basically telling the model to think step by step or show its work.
Like in a math class.
Kind of. Instead of just asking for the final answer to a complex word problem, you prompt it with something like, solve this step by step. The model then generates the intermediate reasoning steps it took to arrive at the solution.
Why does that help?
It seems to force the model to break down the problem and follow a more logical path. It reduces the chance of it jumping to a wrong conclusion. It also makes the reasoning process more transparent for us to check. Even smaller models perform much better on reasoning tasks with COT.
That's fascinating. Forcing it to talk aloud makes it smarter. Okay. And prompt chaining. This sounds like it addresses those token limits we talked about.
It does exactly that. If you have a really complex task that requires more processing or context than fits in the model's single context window, you break it down into smaller sequential steps.
So the output of one prompt becomes the input for the next.
You got it. Maybe the first prompt summarizes a long document. The second prompt takes that summary and extracts key entities. The third prompt uses those entities to draft an email. You chain the prompts together to handle complexity that exceeds the single prompt capacity.
Clever workaround. Okay, so prompting guides the task. What about controlling the style or nature of the output? That's where parameters like temperature come in, right?
Absolutely. Prompt parameters are like dials you can turn to influence the generation process. Temperature is probably the most common one.
And it controls randomness.
Yeah, basically. When the model is deciding the next word, it assigns probabilities to all possibilities. Temperature tweaks those probabilities. A low temperature, like zero point 0.1 or zero point 0.2, makes the model very conservative. It strongly favors the most probable words.
Leading to more focused, deterministic, maybe factual output.
Exactly. Good for coding or summarizing facts.
Mm-hmm.
A high temperature, like 1.0 or higher, increases the randomness. The model is more likely to pick less probable, more surprising words.
Making it more creative, diverse, maybe even a bit weird.
Can be, yeah. Good for brainstorming ideas, writing poetry, more creative tasks. You have to be careful, though. Set it too high, and it can become incoherent. Default is often around 0.7 to 1.0.
Okay, temperature for creativity randomness. What about the output token limit? We know it sets the maximum length.
Right, it caps how long the response can be. Shorter means faster and cheaper.
But you mentioned a risk if it's too short.
Yeah, especially if you're using chain of thought or the task needs detailed explanation. If you cut the limit too aggressively, the model might get cut off mid-thought before it reaches the actual conclusion or the most important part of the answer. You need to give it enough room to think.
Good point. What does the seed parameter do?
The seed initializes the random number generator that the model uses in its sampling process, especially when temperature is above 0. Setting a specific seed value helps make the output reproducible.
So if I run the same prompt with the same seed multiple times, I should get the same answer.
Mostly, yes. LLMs aren't perfectly deterministic due to some low-level factors, but using a seed makes the results highly consistent, very useful for testing, debugging, or when you need predictable outputs.
Okay. And lastly, top P. The sources say it's similar to temperature, but works differently. How?
Right. Top P also controls randomness, but via a different mechanism. Instead of adjusting all probabilities like temperature does, top P sets a cumulative probability threshold.
Meaning?
The model looks at the possible next words, ranked by probability. It then keeps adding words to the potential selection pool, starting from the most likely, until the sum of their probabilities reaches the top p-value, say 0.9 for 90%. It will then only sample from that reduced pool of likely words.
So if one word is overwhelmingly probable, like 95%, the pool might just contain that one word. But if probabilities are more spread out, the pool will be larger.
Exactly. It dynamically adjusts the size of the sampling pool based on the model's certainty at that step. Lower top P, like 0.5, means more conservative, focused output. Higher top P, like 0.95, allows for more variety, but perhaps in a more controlled way than just cranking up temperature.
And the advice is usually to adjust temperature or top P, but not both to extremes.
That's the general rule of thumb, yeah. They interact, so usually you pick one primary lever for controlling randomness and fine-tune that.
This gives us a lot more control than just typing a question. Prompting strategies plus these parameters really let you steer the model.
It's crucial for getting good results consistently.
Okay, for our final section, let's ground all this theory in some specific examples, looking at Google's generative AI tools, particularly the Gemini versus Gemma distinction.
Yeah, understanding the difference between Gemini and Gemma is fundamental if you're working in the Google ecosystem. It really highlights that core choice, managed service versus self-managed model.
Let's start with Gemini. What are its key characteristics?
Gemini is Google's family of closed models. This means Google manages everything, the training, the infrastructure, the updates. You access it purely through an API.
You can't download the model itself.
Correct. A big advantage is that it's inherently multimodal, designed from the ground up to handle text, image, audio, video inputs together effectively, and it comes bundled with useful proprietary Google integrations via the API.
Like the grounding feature we'll talk about.
Exactly. Features like grounding, easy structured JSON output, function calling, those are built into the Gemini API experience.
So Gemini is the choice for someone who wants the latest powerful multimodal capabilities delivered as a managed service without worrying about the underlying tech.
That's a good way to put it. Convenience and cutting-edge features via API.
Now contrast that with Gemma.
Gemma represents the other side of the coin. Gemma models are open weights models.
Meaning you can download the model parameters.
Yes. Google makes the model weights publicly available. This is huge for portability. You can take Gemma and run it on your own hardware.
Like on premises.
Yeah.
Or in a private cloud.
Anywhere you have the compute power. This is critical for organizations with strict data privacy needs, regulatory requirements, or air-gapped environments where data absolutely cannot leave their control. It also avoids vendor lock-in.
But the trade-off is
Yeah,
you have to manage everything yourself.
entirely. With Gemma, you get the model weights, the engine, but you are responsible for the infrastructure to run it, the security around it, integrating it with any tools or data sources you need. It's maximum control and flexibility, but requires significant technical expertise and effort.
In modality, were early Gemma models text only?
Older versions were text-to-text, yes, but newer Gemma models, like Gemma 3, are also being released with multimodal capabilities, closing that gap somewhat, but still requiring self-management.
Okay, so closed managed API, Gemini, versus open self-managed portable Gemma. That's the core difference.
That's the fundamental choice.
Let's talk about Vertex AI, Google's platform. And that concept you mentioned, grounding. What is it and why does it matter?
Grounding is a technique used especially within Vertex AI, with models like Gemini, to improve the factual accuracy and reliability of the AI's responses.
How does it work?
Instead of letting the LLM generate answers based only on the patterns it learned during its massive but potentially outdated or biased training data, grounding connects the model's generation process to a specific, verifiable source of information.
Like Google search
Yeah.
or a company's internal documents.
Exactly. You tell the model, before you answer, check this specific knowledge base or consult Google search results for the latest information. It forces the model to base its answer on or cite real-time verifiable data.
And this directly tackles the problem of hallucinations, right? Where the AI just makes stuff up confidently.
Precisely. Hallucinations are a major risk with LLMs. Grounding is a key strategy to mitigate that risk by anchoring the output in reality, making the AI more trustworthy, especially for enterprise use cases.
Okay, and Vertex AI Search is presented as an out-of-the-box system that uses this, like a pre-built RAG system.
That's a good description. Retrieval Augmented Generation, RAG, is the general architectural pattern. Retrieve relevant information first, then use that information to generate the answer. Vertex AI Search bundles this RA capability.
So it connects the LLM, like Gemini, to your data sources automatically.
Yes, it provides tools to easily index your structured or unstructured enterprise data or leverage Google's web index, and then uses that data to ground the LLM's responses when users ask questions. It saves companies from having to build complex RAG pipelines from scratch.
Allowing them to build custom internal search, power their website search with AI, search media.
All those use cases. It integrates LLM intelligence with reliable information retrieval.
Okay, shifting gears slightly within the Google ecosystem. Agents. What's the difference between Gemini Gems and Google Agent Space?
Think scale and purpose. Gemini Gems are like personalized mini agents or custom instructions that individual users can create within the consumer Gemini interface, similar to GPTs and ChatGPT.
So for personal productivity, like help me practice Spanish vocabulary.
Exactly. They're user-defined shortcuts or specialized assistants for individual tasks. Google Agent Space, on the other hand, is an enterprise platform.
For managing AI agents across a whole company.
Right. It's a secure, shared environment where businesses can build, deploy, manage, and govern specialized AI agents used by their employees or teams. Think of it as an enterprise-grade, isolated hub for leveraging custom AI tools consistently and securely at scale.
So gems are personal, Agent Space is enterprise.
Got it.
Finally, the customer service agents. Agent Assist versus conversational agents. Dialogflow CX.
The key here is who the AI is helping. Agent Assist is AI helping the human customer service agent.
A co-pilot for the human.
Exactly. It runs alongside the human agent during a call or chat, providing real-time help like summarizing the conversation automatically, suggesting relevant knowledge-based articles, Knowledge Assist, or proposing context-aware replies, Smart Reply. It makes the human agent more efficient and effective.
It augments the human, doesn't replace them.
Correct. Conversational agents, typically built using Dialogflow CX, are designed to be the agent. They handle the entire customer interaction autonomously.
So this is the chatbot or voice bot that replaces the need for a human for many queries.
Yes. These are sophisticated, often complex systems designed for self-service interactions, automating the customer support role through predefined conversational flows and AI understanding.
Agent Assist helps the human. Dialogflow CX is the automated agent. Clear distinction.
Very clear functional difference.
Wow, okay. We've covered a huge amount of ground. from the fundamental hierarchy of AI, ML, DL, Gen AI,
Through data types, learning methods like supervised and unsupervised,
into foundational models, transformers, tokens, fine-tuning like PEFT,
prompting techniques like chain of thought, parameters like temperature.
and finally grounding it with specific Google examples like Gemini versus Gemma, grounding, Vertex AI search, and the different agent types.
Hopefully having these definitions clear and understanding the relationships between them gives you that solid foundation we talked about.
Yeah, you should now feel much more confident navigating these terms, whether you're reading an article, talking to vendors, or planning a project. The precision really matters.
It absolutely does.
Before we wrap up this deep dive, I do want to come back to that point about the LLM's inner workings. That mystery element, it feels like the most profound piece from the source material.
The black box nature of complex reasoning.
Right. We've defined them as prediction engines. We know the transformer architecture. We can control them with prompts and parameters. But the sources are clear. Researchers still don't fully understand how these incredibly complex neural networks actually produce their most sophisticated outputs, that emergent reasoning.
We can observe it, measure it, even replicate it with a seed, but tracing the why through billions of connections is often beyond our current capability.
So the final thought we want to leave you with, the listener, is this. We're building so much on top of these powerful AI systems. They're transforming industries, generating knowledge, mediating our interactions.
What does it truly mean for us as individuals, as businesses, as a society, when our most advanced, most influential tools operate at their very core with this element of profound, currently unexplained mystery? How do we build responsibly on something we don't fully comprehend?
It's definitely something to reflect on. Thank you for joining us for this deep dive into the AI glossary. We hope it's armed you with clarity. We'll see you next time.